Alright, I've been battling with technical issues. Let us see if I can maintain a state of calm. So, last week, or this week, since I'm recording this on Friday, we talked about, we went through a lot about, basic neural networks. We talked about what a neural network is. We kind of talked about gradient descent in regards to them. We talked specifically about formulating them with matrix notation, right? And we talked about how NumPy, which is a Python library that gives us access to fast 2D arrays, or efficient 2D arrays, and then like fast operations on those 2D arrays in C, like we can use that to write code in matrix notation that will be easy for us to read and then really fast because NumPy uses C, right? And we ended all of that, and we talked briefly about stochastic gradient descent. Stochastic gradient descent is the specific training algorithm we're using, that looks like this, right? Pick a sample, compute the activation, compute the loss, compute the update, apply learning rate times update, where learning rate is some, small real number, right? 0.1, 0.01, something like that. And we ended looking at this code, right? This code is, with obviously the exception of this line, where we just sort of crossed out the process of getting a data set, this code is a complete implementation of a single layer, unbiased neural network, right? And we didn't actually see this running. So this week, we're going to see this code in operation, right? We're going to talk about this code, and then we're going to see it run. So, we have our weight matrix right here, and I am initializing it to be a bunch of uniformly distributed random values between negative 0.3 and 0.3. There are much smarter ways that I could do this. In general, we are often going to want our initializations to be small real values with an average of 0, right? And we'll talk about some strategies for better initializations later. So this is the height of my weight matrix, and this is the width of it. So it is a 1x2 weight matrix. And if we remember, right, our matrix multiplication, if our input is going to be a column vector and we're going to matrix multiply them, this means that our network is mapping 2 inputs to 1 output, right? 2-item column vector of inputs, a 2-item row, and 1 row, right? So 1 real output of this multiplication. Here I'm defining a function to serve as the here I'm defining the derivative function, right? So if we remember our weight update, which is right here, that weight update needs the derivative of our activation function, right? So if our forward pass is activation of weight matrix times input column vector, then to do our weight updates, we need derivative of that activation function. I have used tan-h as the forward pass, or as the activation function for the forward pass, so I need the derivative of tan-h. And it's d underscore tan-h because people write derivatives that way, right? Sort of, technically I think it's supposed to be a delta, right? But delta tan-h. And again, just as sort of a fact that we're not really going to get into, but just recall from calculus. So, derivative of tan-h of x is 1 minus tan-h of x squared. Right? And so the fact that tan-h appears in both of these, if we wanted to be clever, we actually could do some caching here, but we're not really going to worry about that for this simple thing. Right? So, I've got my learning rate, which is probably smaller than it needs to be. For this simple network, we could get away with a larger learning rate, but 0.01 will be reliably stable for us. I'm using, right? I am updating 100,000 times. Yes. I'm stupid, right? Moving decimal points in my head, but yeah, 100,000 times. We are going to use the Python random module to pick a random element, right? A random input and label, x and d, a random input and label out of our data set. So I am using tuple unpacking here, which means that I am assuming that that data set is a list of x and d pairs, right? I'm assuming it looks like this, where these are tuples, right? I'm hoping that you've seen tuples before. We will also see when we move to working with TensorFlow that we're not really going to build our data sets like this, but this is a convenient way to store our data set right now, right? So the random.choice is going to pick one element out of this list, one of these tuples, and then that tuple is going to get unpacked because of this comma, right? This comma used with this equals. That tuple is going to get unpacked into this x and this d, okay? We're going to compute our pre-activation given our input. So this is that, right? This is this part. And then we're going to apply the activation function. And a student asked in class, why do you keep using tanh? There are other activation functions. Tanh is just kind of a reasonable, well-understood one, right? So I've arbitrarily picked tanh as my activation function. I'm going to apply it here. And that gives me my output. Then, so notice, so then we're going to do our backward pass. Come back to that in a second, sorry. In the backward pass, right, this is just the math that we had earlier, right? Yeah, right. Well, okay, hold on. Let me clear some space here. So this backward pass is just the math that we had earlier, right? We wrote d minus m f prime y x, right? So this backward pass is the math that we invoked the daemon calculus to get earlier, and then we apply our weight update, right? Our computed weight updates times our small learning rate. So we talked about, right, the loss function and sort of the derivative of a parameter with respect to the loss. Notice that we don't actually compute L, right? We do not actually compute L right here. We don't need to, right? It's sort of implicit. We know what the derivative of our loss with respect to a parameter is. If we know that, we don't need, in this scheme, to actually directly compute L. It won't hurt anything, right? It's just a little bit of wasted computation that we don't need to do. So, have I fully disengaged pen writing mode? Come on, advance. All right. Here is a possible set of inputs. Notice, so my notation here is kind of bad because I think some of these columns shouldn't exist. So notice that these are still like two-dimensional brain fade, sorry. These are still two-dimensional arrays, even though there's only one thing and two things in them, respectively, because they need to count as matrices, right? So here I am learning OR as a rule. I'm just trying to train my network on the rule OR. So when both the inputs are 0, we want to so OR, right? I literally just mean the OR logical rule. Right? This OR. So treating this as if it's some kind of real valued function defined on all R is perhaps a little dubious, right? But I am basically trying to train it to learn these points because So but I am trying to train it to learn this rule. So notice, I believe I've talked about this before with at least one of the groups, right? Notice that I have written 1 for true over here, right? But over here I'm using 0.75 to mean true. That is because, right, tan h looks like this. It asymptotically approaches 1 at positive infinity. If I used 1 here, like you would sort of really expect to with OR, I would encourage the weights to explode, right? They're trying to reach, so they would be trying to reach positive infinity for that weight for y, the pre-activation. To get tan h to reach 1, that's going to cause my weights to explode, which will dramatically slow my learning down. That's bad. I actually, for reasons, again, not to keep saying this, but for reasons we'll come to later, I kind of want to try to keep the network over here as much as I can in the semi-linear sloped bit. And so I've moved my output label target in here, right, to a part where it's still curved, that is still inside of like the non-infinite range of tan h. And we find out that if I run this thing, which we'll do in a moment, we get output like this, right? So what I've done here is I've just evaluated the network at each of the input points. We see that it learns to produce 0 pretty well. Excuse me. It actually would have to, because it's unbiased. We'll talk about that. We see that it's sort of close-ish for the condition where one of these is on, and we see that it's a little bit far off for the condition where 2 of them are on. So I actually trained this for a long time. If we look at the loss, yep, it looks like this. So if you're wondering if maybe the reason that it didn't converge is that I didn't train it long enough, notice that the loss shoots down extremely quickly, and then it's sort of, let's see, noisy, right? This should be, lean forward and squint at your screen. This is going to be in 1080p, so you should be able to lean in real close and see that that's kind of jagged, right? But it's not really moving much. It's staying pretty flat. This is essentially the best you're going to get out of this architecture. And there's actually a mathematical reason for that, right? Remember that we have one weight matrix, right, with 2 items in it, and then 1 column vector of input, right? So by asking the neural network to get the same activation when both of the inputs are 1 as when either of them are, think about what I'm asking it to do. So I've got some W here, and some W here, and I've got 0, 1. What I'm telling it that I want it to do is I want it to find some W1 and W2 such that 1 times W1 plus 0 times W2 equals 0.75, but so does 0 times W1 plus 1 times W2, and so does 1 times W1 plus 1 times W2, right? Is there any assignment of W1 and W2 such that all 3 of these products equals the same thing that is not 0, right? So technically, if we assign all of these the value 0, then they would all equal the same thing. It just wouldn't be what we want, right? Is there some non-zero assignment of these things such that they will all be equal? And the answer is obviously no, right? Think about for a second why the answer to this question has to be no. This is actually, for this reason, this is actually the best this network can ever do, right? It doesn't have the computing power, it doesn't have sort of access to enough nonlinearity to do the thing that I'm asking it to do as accurately as I want it to do, right? So what we're kind of seeing here is that even though this is a very simple problem, it is, for very solid mathematical reasons, beyond the ability of our single layer network to ever do. So here I'm going to try to train it to learn the XOR rule. XOR, or exclusive OR, is this. Oops. I mean, as you can see, right? But XOR is true, whoopsie, whenever one of its inputs are true, but false when neither or both of them are true. Right? And we see that the network just does real bad on this. Just kind of whoopsie doodle, goes nuts. Although, notably, again, it is managing to get the zero case precisely. And we'll talk about why that is momentarily. But it's just doing a real bad job trying to get this to work, right? And if we look at that graph of loss, it's insane, right? We don't have that nice structure where it just sort of immediately goes to the best it can possibly do and then just kind of oscillates because the different updates are pulling it in different directions. In this case, it's just nuts, right? And again, it's the same problem, right? We have two weights, right? And what we want is some assignment of, what we want is some assignment of W1 and W2. Brain fade. What we're trying to get it to do is some assignment of W1 and W2 such that W1, 1 plus W2, 0, right, is 0.75. And then also W1, 0 plus W2, 1 is 0.75. But W1, 1 and W2, 1 is 0. So if you imagine the neural network in some intermediate state, these weight updates, right, are going to tend to pull W1 and W2 up, right? These are going to pull W1 and W2 up. This one is going to pull W1 and W2 down, right? Because here, so these weights, W1 and W2, have to go to 0. They have to both be 0 to make this rule work. But they have to both be 0.75 to make this one work. And so both of those updates pull the network in different directions, and it goes nuts, right? It does this. Come on. Whoops. Right? It does that. And that's just kind of the best it's going to get. And again, the problem here is that our very simple two-layer, our very simple two-weight, one-layer network just doesn't have the computational power to do this, right? It's trying to find solutions, but mathematically no solution exists. Well, okay. So what we want it to do, we're going to need to do, is add a layer.